Hello everyone, welcome to this session. In this session, we will talk about global and local optimization. So let's see global optimal solution, which is the first concept. So let's consider in an optimization problem. I want to find the maximum of fx and x belongs to omega, which is a search space. So for each x, we can call it a point, an individual, or a solution. Later, I will call it like that. These are the same thing. All means an element in the search space is an x. So we say x is called a global maximum solution. We are doing maximization now. If for any x in the search space omega, the fx is smaller than or equal to the fx star. So x star, in this way, x star is a global maximum solution. So it's quite intuitive, right? So we can see the fx star value is larger than, or at least not smaller than, all other points in the search space. That's why it's a global optimal solution. An optimization problem may have more than one global optimal solutions. So, for example, the sine function, if we cut a piece, we can find multiple global maximum or global minimum, right? Consider we do maximization or minimization, right? So then this is a concept of global optimal solution. Then we can consider the opposite one, local optimal solution. But to know local optimal solution, we first need to understand the concept. We call it a neighborhood. So a neighborhood is a number of points around a target point. Let's say it's x. The neighborhood of x is a number of points around it, or we say close to it. So how to define the close? So close depends on two things. First is the problem itself. So how to represent the solutions. The second is your decision. So let's see an example first. So here we are in the real space, two-dimensional, and a neighbor of x I defined is that if the Euclidean distance between x1 and x2, we call this xi, this vector, is smaller than 0.1. Smaller than 0.1, right? So consider if x is 1, 0, then what? Then how to define the neighborhood according to my choice of 0.1 and the problem itself with a real parameter. So we can see that is x1 minus 1 to the power of 2 plus x2 minus 0 to the power of 2 smaller than 0.1 to the power of 2, right? So this is a circle with a radius of 0.1. Another neighborhood in this time is not two-dimensional real data. We become binary data, 0 or 1. We have, let's say we have 4 bytes, is a x1, x2, x3, x4. Each of them is either a 0 or is a 1. Now we will define such a neighborhood. So how to define it? We can say the Hamming distance between x and an xi is 1. So we can see, let's say if x is 1, 0, 0, 1, then the neighborhood is what? We just change any 1 to 0 or any 0 to 1. So we can see by changing it, we generate 4 solutions. So these are the neighborhood of 1, 0, 0, 1. The problem itself make sure that this is a binary. This is a neighborhood definition is okay with a binary representation of the solution. And my decision is only Hamming distance is 1, right? So we can see this one, we use a flip, then we generate a neighbor. So now another kind of neighborhood for permutations, right? So let's see if we have a permutation, D is from 1 to 4. So 1, 2, 3, 4, 1, 3, 2, 4, etc. All the permutations. So then considering this problem, how to define the neighborhood of a candidate solution? right? So what we can do is that we can do a single swap or multiple swaps, right? So this distance is decided by the swap. So we can see the swapping is decided by the problem, and a single swap is decided by me, right? So let's see. We have 2, 3, 4, 1. Then the neighborhood of this candidate solution is what? Okay, it's like this, right? So we randomly select two elements of them, and then we swap them. Single swap. So in this example, we use a swap to generate a neighbor, right? So now we understand the concept of neighborhood. So then we can talk about the local optimal solution. So local optimal solution is a point that is not worse than any other points in its neighborhood, not in the whole search space, in its neighborhood. So this depends on what neighborhood you select, right? So if you select the search space as the neighborhood, then what? Then the local optimum is a global optimum, right? So that's why a global optimal solution is always local optimum, because the neighborhood is defined by you. If you define the neighborhood is a whole search space, then that is a global optimal solution. And if we put it opposite, is this correct? A local optimal is always global optimal. So as we can see here, so there are 3 optimal points. So this is a global maximum, there's a local maximum, as well as this, also local maximum, right? But however, these and these are not global maximum. They are only local maximum, right? So now we understand the concept of a global maximum and local maximum. So we can talk about 2 kinds of optimization. So let's talk about the local optimization first. So local optimization, often we aim to find an optimal point, but this point is local, right? So this should be the optimal solution from a specific region of the search space. Often we show a starting point to define where is a specific region. So for example, in this figure, if I say I started from here, okay, I might get this local optimum. So this is a region. If I start here, I may come to here. I start here, I may come to this local optimal solution, and this is a global optimal one as well, right? In contrast, the global optimization, we aim to find a global optimal point or the points of the whole search space. It may have a starting point or may not, or in many cases, especially in engineering, maybe only the search space is provided, and we need to find the global optimal solutions from the search space. And also when we carry out global optimization, we don't guarantee we will find the global optimal solution. Remember this. So we try to get it. We try to obtain the global optimal solution, but we may not. And the algorithm may have some operators to avoid being trapped into local optimum. But we can't guarantee we can find the global optimum when we carry out global optimization. Right. Now, at last, I would introduce the unimodal and the multimodal optimization problems. So this depends on the global and local optimum. So unimodal, we also call it convex. This means the landscape only have a single optimal value. So for example, if we consider minimization, you can see here, right? So the only local optimal point is here, right? In contrast, for multimodal, unimodal, multimodal, when we consider multimodal, the landscape has more than one local optimum. Show you an example is here, right? If we consider minimization, we have quite a few local minima, but only one is global. Right? So this is a unimodal and multimodal optimization problems. Okay, that's all for this session. Thank you very much. Bye-bye.